Right, so I showed you a lot about this cozy spectrum and how we can use them to get coupled protons. And I showed you how to manipulate some of these. I'm just going to run through some of these objectives that I had for today and see which we covered. So I showed you how to expand a spectrum, right? So you should be able to do that. I showed you how to increase and decrease intensity by using the roller on your mouse. So you should know how to do that. I showed you how to put the baseline at the center or at the bottom of the spectrum. So you know how to do that. I didn't show you this. I'll show you this now. How to do external projections. And I discussed how to correlate proton-coupled resonances in the cozy spectrum with you. Right, so the only thing that's left for me to do now is show you how to use an HMBC and an HSQC, how to do the external projection, and how to use your HSQC and your HMBC to assign the molecule unequivocally, all the singlets in your molecule. So every carbon atom and every hydrogen atom, you must have at least an idea of where those protons and carbon resonances lie in your spectra, right? And that's what you're going to use to convince someone that you've made a particular compound, or that this is the structure of the compound that I've made or I found, right? Remember that when I first started off, I did natural products. I got compounds from plants, and I was able to say that this compound that I found in this plant, there is the structure of this compound, and this is why it is the structure. And you can see that I can actually spend a whole lecture, maybe 45 minutes to an hour, looking at one spectra, right? That's why I say that sometimes when you have a 10 or 15 minute talk, don't put 15 slides there. You can actually talk on one slide for about 10 minutes, by just particularly understanding that particular slide. So I'm going to go back now to the spectra, and I'm going to start now with the HSQC spectrum. All right, so this was your carbon, experiment number 10. Experiment 11 was the proton. We've looked at the carbon, we've looked at the proton. Experiment number 12 was your cozy, we've looked at that. Let's look at the HSQC spectrum of this molecule. So this is the HSQC spectrum of this molecule. I'm just going to mess this up a bit. Just to show you something, so I'm just going to mess it up slightly. Okay, I'm not getting the nucleus to match. But what I want to show you initially is that sometimes you don't get, and I think we have it in this particular session. So, but sometimes if you load your spectrum and you don't see the spectrum that you want to see. So in this particular case, your proton NMR spectrum must be on your x-axis, and your carbon-13 NMR spectrum must be on your y-axis. And in some cases, when you load this up, you don't see the carbon-13 NMR spectrum on your y-axis. So in which case, I'll need to highlight this to make this active, right-click, right, and do an external projection on this, right? And the external projection, I must know what particular experiment is my carbon spectrum and my proton spectrum. So you see here, my carbon spectrum was 10, so this is correct. I was trying to actually make it incorrect here. Not allowing me to make it incorrect. Let me just try internal projection. Right, so now I've messed it up a bit. And let's see if I'm allowed to now get the right spectrum here. So the right spectrum I know is experiment number 10, where I've actually had my carbon-13 in there, right? And can you see now it's gone back to my carbon-13. So that's my correct spectrum, right? So just to run through that again, right? So when you load it, sometimes it appears like this, right? So this is, you can actually see is not the right spectrum in this particular case. Right, so this is some other experiment. I don't know what this is, but you need to now load your carbon-13 NMR spectrum on your on your y-axis and your proton NMR spectrum here. So I right-click here, I go to external projection, right, to load it from elsewhere, I see that this is the wrong experiment. Because 13, remember 13 was your HSQC. I want to make it my carbon spectrum on that axis. My carbon spectrum was experiment number 10. If I look at this particular one that I'm seeing here, let's see what this is. So this is the right spectrum, the spectrum number 11, right? But if you want to mess it up a bit, right, so I'm gonna probably just try and mess it up, right? So I want to get the right spectrum. I want to get the proton spectrum here. If I look at this, I don't have the right spectrum here. I just have this experiment number 13, which is the HSQC here. I want to put my proton NMR spectrum, and my proton NMR spectrum here was spectrum number 11. Right, so I got my right spectrum here. I want to have my proton NMR spectrum, spectrum number 11, on my x-axis, and I have it. And I want to have my carbon NMR spectrum on my y-axis. I loaded it. Experiment number 10, experiment number 11. Right. So just to run it again, right-click, external projection, and then you put the right number in here. All right, so that's how to use the external projection. So that's how to do an external projection to get the right spectrum on your screen. All right, so now we're going to go back to the HSQC spectrum and analyze this. Now, an HSQC spectrum will correlate every protonated resonance to a carbon spectrum. So every protonated resonance that you see here will have to match one of the carbons to tell you that this proton is on that particular carbon, right? And we assigned some of these. So we assigned that, we assigned that, we assigned that, we assigned those, we assigned those, we assigned that, and one of these. We can now pick out where those carbons lie in here. And remember, it's quite interesting now because I discussed something with you yesterday when I discussed coupling between fluorine and carbon. And when I discussed coupling between fluorine and carbon, I identified these carbon resonances. And in today's lecture, I identified the proton resonances. So we're going to verify now, and I said tentatively previously, because what we're going to do now is we're going to see if whether what we did tentatively is actually true or not by using this HSQC spectrum, right? So again, I only have peaks in this region and peaks in this region. So I'm going to expand that particular region, right? And have a look at that particular region. All right, so what I can actually see now is if I increase my intensity here, that these peaks are actually quite pronounced, right? So I can also increase the noise. As I said, now I see all the houses, all the rooftops, all the rivers and everything else. And now I'm decreasing it just by using my roller on my mouse. And what I want here is for every resonance to have a particular peak, right? So a resonance must be equivalent to a particular peak. So I must correlate a proton resonance with a carbon resonance. I must correlate a proton resonance with a carbon resonance, right? And the same proton resonance with a carbon resonance and everything else, right? So all of these must be correlated to something in here. Right now, I was playing around with this yesterday and I messed this up, particularly messed it up because I wanted to show you how to fix something if it's messed up, right? So what you'll notice now, and if you look at this very carefully, this resonance will have a peak that's corresponding to this carbon, right? The closest one I have is this particular resonance, but it's slightly off. Can you see it's slightly off in this case? So this peak should actually correlate to a peak that's at 7.43 and 110, right? The carbon correlation is fine because the carbon correlation, you can actually see it's spot on to that particular carbon. But the peak needs to be in the center of this particular resonance here. And this resonance, and I'm looking here, right? Because this is actually the columns that it is in. So downways is a column. So if I'm looking at this particular resonance, I'll look at this value here, and it should actually be, so the calibration should actually be here, right? I can also expand this particular resonance so I can see it very, very clearly. And can you see that I should actually have the center here appearing here, not to my left, right? So it's actually a messed up spectrum. I want to correct it. So I know now that this resonance must be 110.7. It is 110.7 for the carbon, but my proton is off because my proton should be at 7.42 or 7.43, but it's now sitting at 7.45, right? So I want to make it at 7.43. So I go to calibrate my axis, right? And if I calibrate my axis, I'm going to click on the center of this peak because I want the center of this peak to appear here. And if I click on the center of this peak, you can see my 110.7 is fine, but see my 7.45 is not fine. That should have actually been 7.428 or somewhere around there, 7.4. Right, so I'm going to alter that value. I'm going to click OK. And can you see now, I have exactly the same peak. And if I look here, I can see now that this peak corresponds nicely with this carbon peak here. So I've actually calibrated my 2D spectrum. All right. I'm going to just expand this a bit. Now you can see all my peaks are in line with carbons and protons. That's in line with that, that's in line with that, that's in line with that, that's in line with that. And I've got 1, 2, 3, 4, 5 here. I'm counting this twice because remember we said this was a more intensity. So there are 2 protons, there are 2 carbons here. So we counted that twice. That's 2, 3, 4, 5. And remember we had 5 protons in this particular overlapping region. All right. So I'm going to match each of these. So the first thing I'm going to do is match this particular double doublet because I know that this particular double doublet is this proton here. And this carbon we said yesterday is going to be split into 20 hertz by this fluorine atom. And this is one of the ones that we said was split into 20 hertz. So let's have a look, right? We said that, that, and that. So of the 3, I know that the carbon resonance is correct. So yesterday we identified this carbon resonance as being for these 2 carbons. Today we identify the proton resonance as being for these 2 protons. And can you see now that the proton resonance and the carbon resonance actually correlate to each other? So that's a nice correlation that we have here. I'm going to do another one, right? We said yesterday that this particular peak was a carbon resonance that was ortho to this fluorine atom. And today we said that this particular double doublet was due to this hydrogen. So yesterday I didn't know whether this carbon or that carbon was either that or that. But today I can know exactly that this particular carbon being correlated to this particular proton resonance with that splitting pattern is unequivocally this carbon atom here. So I can immediately identify this carbon atom just by what I did today with the coupling constants. So that correlates to that, and that's these 2 carbons here. That correlates to the proton there and the carbon on there. And I said that this doublet of doublets of doublets was due to that carbon. And it must correlate to this particular resonance because that's the only other carbon that we have with the 20 hertz coupling constant. And let's see if we're correct. So there's my peak. And can you see it's spot on? I have a correlation to that carbon and I have a correlation to that. So that proton resonance, that proton resonance, and that proton resonance were all coupled to the fluorine, right? And in an ortho position, which also coupled the carbons to about 20 hertz each. And each of those correspond to each other. Nicely there, nicely there, nicely there. The next one I'm going to move to is this particular one, right? Now this one I said must either be on this particular ring because of the cis coupled protons. So it's either that proton there or that proton there. So all I can do now, I can't say which proton it is. It's either that one or that one, but I can say that the carbon atom that that proton is on must be here, right? So this proton and this carbon is either there or there. And when we discussed the HMBC just now, I'll show you how we can actually see whether it is one of those or not, right? So we can positively identify them as one of those, right? So all I can do is now identify the carbon that this proton is on, and the same here with this double bond, right? This is one of those. So I can say one of these carbon resonances must be here, right? Because it's correlated to one of these here. And then the 5 carbons, what's on these 5 protons, or the carbons on these 5 protons, must be there, 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 and there. Now you can actually look at this and you can say, okay, between 125 and 138 or so, I want to go back and look at the carbon for 125 and 138. Because what I can see now is that I have a bunch of things in here. But let me take you back to 135 and 128 and show you what else we can actually do and what's actually quite neat. Right, so remember I said we can expand this region. I'm going to look very specifically here, right? So now I'm looking at this region here and I'm seeing that I can actually get some other information just by looking at these coupling constants. Because remember yesterday I said that no coupling might mean it's not next to any fluorine atom. And then I've got a coupling here, which was about 8 Hertz, right? Which means a metacoupled proton. Sorry, metacoupled carbon. Another 8 to 10 Hertz here, which means another metacoupled proton. And then a smaller coupling here, all right? So that coupling is a bit smaller here, about 5 Hertz or so. 5 to 6 Hertz, right? So I can see that these two, the 131 and the 132, are metacoupled carbons, all right? So just remember that that's a metacoupled carbon, that's a metacoupled carbon, and this is a smaller coupling constant, so it might be a little bit further away, and then there's a singlet here, so it's going to be very far away from the fluorine atoms. And let me go back now and open my HSQC. All right, so I'm back here with my HSQC and I'm now looking at this particular area and I'm saying, okay, what's nice is that I've got the 5 protons on here. So I can say that these 2 metacoupled protons, right? One is this, because these are metacoupled protons, right? That is also a metacoupled proton here, right? So this is going to be one, that's going to be the other one. And if I look here, there's my one, the one that's intense, the very intense one is going to be coupled. So I can actually work on this and say that the resonance for these 2 protons here must be in this region here. So I can actually say it's not in this particular region or that particular region, it's somewhere here. So I can go very nicely into this mess here and sort of more in-depthly look at this mess. And you can see the other one, a doublet, must be somewhere here, right? And that doublet that's somewhere here is going to be due to your other metacoupled proton here, right? So you've got a metacoupled proton here to that fluorine atom, and you're going to see it somewhere around here, right? So at certain times, what we can actually do is we can look at this particular resonance, and we can actually tease out the doublets and the double doublets in this particular mess, right? Which is a very, very intense thing to do when you're working out NMR spectrum, to actually say that the double doublet in this is actually in this particular mess, and I know where the peaks are. I know that the peak is here and that the peak is here, right? You can see now that I can very nicely and very cleverly look at this particular peak and this particular peak and tell you that the doublet for one of these carbons, right? That's the carbon atom for one of these carbons here. I know that because it was the only one without or very far away from the fluorine atoms. And also, can you see the large coupling constant here between there and there? So I can pick out this peak and this peak as being the doublet. So what was initially a mess because all of the overlapping peaks, I can now get a nice value for that doublet here and there, because I know that that's one of my trans-olefinic protons. All right, so it's just a very advanced way of looking at this particular spectrum. And can you see that the other proton that you have here is in this region here, and that you can see that the doublet is in this particular region. All right, so this you'll notice now, if you very intuitively, I know where to look, but I'll just tell you as well that the only other fluorine-carbon coupling that in this area is going to be this proton here, because this proton is the closest to this fluorine atom. So this proton here is actually here, and that, if I look, you know, I'll take you back to the proton just now and we'll re-look at this, but you see this peak and this peak, but it's a bit ambiguous here. I don't know whether it's that peak or that peak, right? But that and that might actually be the doublet of this, right? So I want to just run back and just show you what we've just done, because it's a very advanced way of looking at these types of things to show you how to pay attention to detail. All right, so what we've actually done now, and what I've said is that if I look at this peak here and this peak here, that's your peak that's coupling to this big one. So let me look at the coupling constant here. That's about 15 or 16 hertz or so, if I do it properly, say about 16 hertz, right? And if I measure the distance between that peak and that peak, right, that's about maybe 14 hertz or so. So I might want to say, okay, maybe it's this particular peak here. Can you see on the other side of that, there's a small particular peak there and here. So it's more highly likely that that is the resonance for your trans-coupled proton. And that this peak and maybe this peak is the resonance for the about 8 hertz that I'm seeing here, is the resonance for this double bond, one of them in here. Right, so we can actually tease it out from this particular one. Right, but those are what we call ambiguous assignments. It's not unambiguous, it's ambiguous because I can't say for certainly. It might be that and that, or it might be that and that, or it might be that and that. So it's a bit ambiguous, but it's roughly a good approximation of where that resonance actually is. Right, so we actually know how to look at a HSQC spectrum. You know how to get the information here. The main thing is that every protonated carbon must be identified, and you can identify all those protonated carbons. All right, now the next thing we're going to look at is the HMBC. This is the last spectrum that we're looking at before we close. Right, so it's exactly the same thing that we have, and I'm going to make sure I have my proton there. I'm going to make sure I have my carbon there. So this now correlates protons to carbons again. But in the HSQC, we correlated a proton directly on the carbon. Here, in this HMBC, we're correlating a proton 2 or 3 bonds away from the carbon. Right? So I'm looking at resonances here, and these peaks here depict peaks that are 2 and 3 bonds away from a carbon. Right? So I'm going to show you how to tackle these very nicely to solve the structure. But before I jump into that, I want to see what we know about the structure and what we don't know about the structure. So I know that proton and carbon, I know that proton, that carbon, I know that proton and carbon, I know that proton and carbon. We don't know much about that and that. Remember we said there were 2 carbons in the NC range, that carbon and that carbon. And I need to see which each of them are. I don't know how to tell the difference between the carbons and hydrogens on this double bond. I don't know how to tell between the carbons and hydrogens on that double bond. All right, I know all these protons and carbons on this ring, but I don't know where this carbon here sits. Right, so I don't know where this carbon here sits. I don't know much about that. I don't know much about that. This here, there's some questions, and that there's some questions. So let's see if I can use my HMBC to now answer all those questions and come up with a good approximation of what my structure is and some good evidence of what my structure is. So I'm just going to put this at my center. And I'm going to put this at my center because I want to look at certain singlets in this particular spectrum. And the first one I want to look at is this carbon here, right? So this carbon here is a singlet carbon, and it's around 130 or so. So it's not that carbon, it's not that carbon, right? The only one it can actually be is it can be this particular carbon here, or it can be that particular carbon there. Now this carbon is para to that fluorine, but this carbon is meta to the fluorine. And when I discussed the carbon spectra, we looked at the coupling constant of this carbon. We said it was about 8 Hertz or so, which was probably this carbon atom here. And if it were that carbon atom, it would be coupled now to either the proton here, or the proton here, in order for me to identify it as being that particular carbon. So let's see if I can identify it to either that, because I know how that looks. That looks like a double doublet. I know this is in the big mess that we have where all the peaks overlap. And I don't know whether this is where the peaks overlap or whether this is that nice doublet that we're seeing. So we're seeing the nice doublet there. I don't know whether that's the doublet that we're seeing. So let me look here, all right? And if I'm looking at this particular, so I'm taking this particular resonance and I'm placing my crosshair on there, and I'm going across now. I can see there's some correlations. Can you see these correlations here in that particular mess, right? And I know that I have peaks in that particular mess. Well, this is one of them, right? This hydrogen is in that overlapping peaks that we have here, right? So I can see the correlation there. I can see a nice correlation here. And this correlation tells me that it's either a proton on here or a proton on there. Now, can I use this to actually say which proton this is? Is it either that one or that one, right? I can't do that because this carbon is 2 bonds away from this hydrogen and it's 3 bonds away from that hydrogen. And in my HMBC spectrum, I can see correlations that are either 2 or 3 bonds away. So what I can actually say at this point in time is that this carbon is definitely here, right? I can say this carbon is definitely here because it's correlating to one of those protons, either that or that. But I can't say for certain that this particular proton is either there or there based on that particular carbon, proton-carbon correlation, right? So get that very clear, that this correlation only will identify the carbon as being here, but it will not allow me to say whether this carbon is unequivocally at that position or that position. So I'm going to investigate this resonance a little bit more and see what peaks I have. So this carbon also, so this proton resonance also has a correlation to something around 110, all right? So it also has a correlation to something around 110, and it also has a correlation to something that I have around 142 or so, all right? Now, remember yesterday that when we looked, we said that there were peaks around here, 142, and we assigned these types of peaks to the different ones, right? So we assigned all these carbon peaks based on what we knew about the molecule. So I'm going to see if this carbon atom here and this carbon atom here can be anything in this vicinity, right? So if I look at this particular one, I notice that it can also be coupled, this proton can also be coupled to this particular carbon that I'm seeing here, right? And it can also be coupled 1, 2, 3 for that particular carbon on this particular double bond. So I can expect to see 2 other protonated carbon resonances, this one and this one, that's correlating to here. And that's what I'm seeing. I'm seeing one here. So this is my one protonated carbon, right? And this is my other protonated carbon, right? So my one protonated carbon and my other protonated carbon. And let's see, one is around 142 and the other is around 110. So let's see what I can actually get from there. So I'm going to go back to my HSQC. One is around 110 and the other one is around 142. And you can see the around 110 proton, or the 110 that I have here, the carbon, must be this double doublet, which we identified as being here. Right? So we identified this carbon as being here, which means that 1, 2, 3 bonds away, there must be a proton resonance somewhere in that vicinity. Right? And we also see that it's also coupled to something that we said is at 142. And 142, we can see that your other resonance that we're seeing here. And that's 1, 2, 3 bonds away from that as well. So if this particular proton was at this position, it's showing a 1, 2, 3 J correlation to this proton. And it's also showing a 1, 2, 3, 4 J correlation to this proton as well. Right? So it's showing two correlations, one here and one here. All right? So it's a bit ambiguous in this instance because we can't clearly say, so the 110 is this carbon that we know for sure, right? We know that this particular carbon at 142, right, must be one of these. So it's probably this one because this one is closer to the double bond than this one, right? So I'm going to tentatively say that 142, this carbon peak here, is this carbon that I'm seeing here. And because it's showing a resonance here, that this peak, this doublet that we're seeing in the proton must be this proton that's next to the quinoline ring. And the other one in the mess must be the other one. All right? Now let's just go back to the HMBC. Right, so I've nicely correlated this peak and I've showed you how I used the correlation here, I've used the correlation here, and I've used the correlation here, all to look at this particular carbon. What I'm going to do now is try and expand this part here to get a little bit more information on this particular singlets that I have. So I dealt with that particular singlet. Now let's see if I can have any more information around all the singlets that I have. Remember, I got another singlet here that I have around, say, about 140 or so. And this singlet that I have here is showing correlations. So can you see the small one here is showing correlations, if I look at them, to this peak and this peak. Now can you see that if I didn't increase the noise so much, I wouldn't see them. So I'm increasing this noise such that I can get what I want. I'm looking for a correlation here. So I'm increasing the noise until I see a reasonable correlation here. All right, and I'm seeing some reasonable correlations. I'm not going to concentrate so much on this because this is in this mesh and I can't see what's going on. But I'm looking at this around 140, 142 or maybe 144 or so. I'm looking at the singlet here. And you can see that it's correlating to that peak and that peak, which I know is that peak and that peak. And the correlation I'm actually looking at now is a singlet correlation, which means it can't be this carbon here. Remember I said there were two NC carbons. It can't be that carbon there. It has to be this particular carbon on this nitrogen, which is here. So this is correlating nicely with that proton, and I'm seeing the two correlations here. And those two correlations make me want to assign, or allows me to assign this carbon particularly to that carbon peak that I have here. All right? So I'm able to unequivocally assign that to that. Now, if you think further on, we had another carbon peak that was a little bit away, right? And I had two there, which means by default now, the other carbon atom must be that one. We'll go back just now and look at the carbon spectrum. But before we do that, I want to take your attention to something else. If I'm looking at this peak here, right? Remember before when I went through the carbon, I said I didn't know whether this was the peak or that was the peak or whether there were noise. And remember, we couldn't pick this peak up in the carbon spectrum. It was too fine, the noise, to actually pick up. It wasn't even picking up when we were trying to label it or identify the peak peaks, all right? But now, if I look at this particular example, what we'll find is that I can look at this in my HMBC. So I'm looking particularly at the singlet that you see here. And if I look at the singlet that you're seeing here, I'm picking up a very nice correlation to this. And because I'm picking up such a nice correlation to this, I know exactly what this is, and that's these two here. All right? So these two protons here are showing a correlation. The only thing you can show a correlation to is this carbon atom that I'm seeing here. So here, I'm actually seeing a correlation to this that allows me to assign this carbon atom here. I've saw these two correlations here and there that allows me to assign that carbon atom here, that singlet there. I've got a correlation here, which is this one, to that doublet, right? So this doublet here, which shows me that this doublet and that carbon atom are correlated, so it allows me to assign that singlet. The only singlet that I don't have any correlations for is this particular carbon, right? So this particular carbon, I don't really have any correlations for that to assign it. I'll just show you that I don't have any by looking at the expansion. So I'm going to look at this particular area here. So we're looking mainly now at this region, right? So I discussed these two peaks with you. I discussed that correlation with you, and I discussed this correlation with you, right? These two here. So these two here and this one here I've discussed with you, and I've also discussed this one, right? This one with you. All right, so we know that the singlet here, what singlet this is. We know this singlet here. We know what that singlet is. We also know that singlet, what it is. We also know that singlet, what it is. And they all correlate very, very nicely to everything else. Right, so this hydrogen correlating to that carbon gives you a nice, that one is known. Your carbonyl peak you can actually pick out because that was very easy to pick out. And these peaks you picked out is the doublets for these carbons, right? So the other peak in that spectrum, we actually don't know, but we're going to now look at the carbon spectrum again and see if we can actually get any ideas now that we know what we've assigned, right? This other peak around 154, we didn't assign that yet, right? So this peak around 154 wasn't assigned to anything. And let's see if I can actually get some information around this peak around 154. This 154, I'm not going to look at the overlapping peaks, but it very nicely shows correlations to two things. And it shows a correlation to this olefinic doublet that we're seeing here, this trans olefinic doublet that we're seeing here. It also shows a correlation to the cis-coupled ones. And if I look at this particular carbon, you can see this carbon is next to the olefinic ones, and it's next to the cis-coupled protons. So it's showing a correlation somewhere here, and it's showing a correlation there. So this particular resonance that I find here at 150 something is actually this particular carbon resonance that I see here. So now I can actually, I know what that is, I know what that is, I know what that is, and I know what that is. All my singlets in my, my molecule is assigned. Right? The only other ambiguity I have now is this particular proton resonance, right? Because this proton has 1, 2, 3 bonds away from there, and I also saw some resonances to there. So I don't know whether this resonance that I'm seeing here is either this proton or that proton. And I'm in a little bit of a dilemma here, because if it were here, it would be 1, 2, 3 bonds away from that carbon, but 1, 2, 3, 4 bonds away from that carbon. And if it were here, it would be 1, 2, 3, 4 bonds away from that carbon, but 3 bonds away from that particular carbon. So remember, I'm seeing a correlation to this one, right? And this carbon atom that we saw here was at this point here. But remember, we also saw something at 110 as well. All right, so I'm just going to expand this part here. So I also saw something at 110 for this resonance, right? And the 110 was actually this particular carbon. So that's the only proton that I'm a little bit ambiguous about. And although I have 4 correlations here, I have a correlation for this proton to that particular carbon. I've got a correlation to that particular carbon. I've got a correlation here around 142 to that particular carbon, right? And I've got a correlation here to that particular carbon, right? So I've got correlations to 1, 2, and 3, and 4. It doesn't really help me much to say whether it's that proton resonance or that proton resonance that I'm seeing here, right? So that's the only little bit of ambiguity I got. And maybe when you go through the spectra yourself, you can actually see, is there any way to unequivocally say whether that's either at the H3 or H4 position, right? So this is the H3 position, that's the H4 position. So maybe look at this a little bit more closely and see how you can actually solve that problem. I'd like to see that in your essays that you're going to write for me. All right, so I think I've actually interrogated this spectrum enough to show you how to use an HMBC spectrum in structural elucidation. I'm just going to go back to my objectives of the sessions, and let's see what we've done. I've showed you how to expand a spectrum. I've showed you how to increase and increase density. You saw how to put baselines at the center and the bottom. I showed you how to do external projections. You saw how to analyze a COSY spectrum. You saw how to analyze an HSQC spectrum. You just recently learned how to analyze an HMBC spectrum, and you learned how to use the HMBC spectrum to assign your singlets. So I think we've covered everything that we needed to cover in these 2 sessions for the NMR workshop of the Chem 751 course. I'm going to stop there, and I'm going to take any questions that you may have for me. Is there any questions that anybody has? You can put your hand up, or you can actually put it on the chat if you're feeling a bit shy to ask me anything. Do you all feel that you can actually tackle this? All right, so let's see how you can actually tackle this when you do your assignments. I'm going to stop recording here, and then I'll talk a little bit about your assignment, right?